And we're live.
Hello, everyone. Welcome to our first NHP seminar given by Professor José Lado today. Before introducing the speaker, let me remind you about our house rules. So to save the bandwidth, I ask everyone to kindly turn their camera off. We, in principle, do not accept questions during the presentation, but after the presentation, during the Q&A, you can use the raise hand button to ask your questions. For those friends joining us on YouTube, I encourage you to write down your questions in the chat box so that one of the moderators will pass your question to the speaker. Same as always, you can find details on our house rules or our code of conduct and further details on our website, so check that out. An important announcement is that our next speaker is Professor Angelo Carollo. He will give a talk on 19th of July, so stay tuned for another exciting presentation in our NHP seminar series. And by this being said, I'm very much delighted to introduce to you our speaker, Professor José Lado today. José got his PhD at INL in Portugal in 2016. He then moved to ETH Zurich as an ETH fellow. In 2019, he joined Aalto University as an assistant professor, and he's working there since then. His main area of expertise is topological and correlated quantum materials, and today he's going to walk us through some of his recent results on static and dynamic topological modes in interacting non-Hermitian systems with tensor networks. With this being said, we're looking forward to your talk, José, and the stage is yours.
Thank you so much for the introduction and for the wonderful opportunity of being here. So I think that I don't have permissions to share now, so maybe you could update it so that I can. Yes, now it's perfect.
It should be now. Yeah.
Yes, yes, now it works. Thanks a lot. Yeah, so thank you so much for the introduction. It is a real wonderful pleasure to be here in this non-Hermitian seminar series, and I think that this is having a really wonderful impact in the community. So please keep organizing these seminars. So my name is José Lado, and today I'd like to tell you how we can compute dynamical excitations in interacting non-Hermitian systems. And specifically, I'm going to show you how we can use tensor networks, a many-body technique that was initially developed for Hermitian systems, to actually tackle non-Hermitian interacting models. So the background for this idea is that in the last few years, we have gotten a huge amount of different types of topological matter. Everything started, of course, with the quantum Hall effect several decades ago. In the last few years, we've seen whole new families of topological states, like quantum anomalous Hall states, including Chern insulators, topological semimetals like Weyl semimetals, of course, quantum spin Hall insulators, topological superconductors, not aligned semimetals, topological quantum insulators, and many others. All those systems are single particle systems. We can understand their topology from the point of view of a single particle Hamiltonian. We look at single particle excitations, we compute single particle topological invariants. But in topological matter, there are two very important open questions, which is what happens when we introduce many-body interactions to topological systems, or whether we can have topology purely driven from many-body interactions, and what happens when we take topological systems and we couple to the environment, or even more exciting, whether we can create topological excitations just by coupling to the environment. And these two major questions has given rise to whole new fields within condensed matter, fields of interacting topological matter and non-Hermitian physics, the topic of this very nice colloquium series. So today, I would like to make a first step in bringing these two ingredients together, in bringing together many-body interactions and coupling to the environment. So the basic idea is that the study of many-body interactions in electronic systems has, of course, a long history, and we currently know that there are many potential possibilities of interacting that can happen in interacting systems. We can have quantum spin liquids arising in quantum many-body systems with interactions. We can have fractional Chern insulators driven by interactions in flat bands like Landau levels, and ideally we can even have parafermions if we have special combinations of superconductivity and fractional Chern states. All these states are a big open problem in condensed matter. We have a lot of understanding on them, but techniques to solve these problems are still in their infancy. In the case of non-Hermitian systems, we have gotten in the last few years a lot of progress in this direction, especially in the direction of single particle non-Hermitian systems. And there are many possibilities in non-Hermitian systems, as you well all know, but let me just point out two of them that are going to be very relevant for what I'm going to tell you today. First one is that we can have non-Hermitian topology, namely the appearance of edge modes coming from coupling to an environment. And the second is that we can have a phenomena called non-Hermitian skin effect, that it's a phenomenon that only appears in non-Hermitian systems and essentially creates that all the eigenstates of your Hamiltonian concentrate on one edge of the system. These two phenomena are well understood or at the single particle level. In the many-body case, we still know very few things about them. So the idea for today is I would like to go in this very specific direction. What happens when we merge these two ideas together, many-body interactions and non-Hermitian topology? And to show you this, I would like to first start by giving you a reminder of tensor networks for many-body matter, namely how we can solve quantum many-body Hamiltonians with these approximate methods. Then I'd like to tell you how we can actually see edge states in many-body Hamiltonians by looking at something called dynamical correlators, that it's a very useful quantity to understand excitations in many-body systems, and that it's very much related with the density of states in single particle Hamiltonians. And then after this introduction, I'd like to tell you about the specific new results that I would like to show you today. First, how we can see edge modes in interacting non-Hermitian systems using tensor networks. And second, how we can see also these edge modes from computing dynamical excitations in these interacting non-Hermitian systems. And before moving on with the physics part, let me emphasize that all the work that I'm going to show you today has been possible thanks for a lot of work done by a lot of people that are not here in the audience. And in particular, I would like to thank Timo Huart for his wonderful work showing that we can actually see edge modes in interacting non-Hermitian systems, and especially the outstanding work of Wanse Chen and the collaboration with Fei Song, where we show that we can see edge modes computed by computing dynamical excitations in interacting many-body models. Good. So let me start by giving you a reminder of how we can understand many-body systems, or how we can solve many-body systems using tensor networks. Many-body systems are very, very challenging, and the reason why they are challenging is actually extremely simple. Imagine that you take the simplest many-body Hamiltonian that you can think of, so a one-dimensional spin chain, a one-dimensional Heisenberg chain. If you take L sides in your chain, essentially the Hilbert space is 2 to the L, even if you consider spin 1/2. What this means is that your Hilbert space is exponentially large, and once you take more than 30 sides, let's say, you do not even have enough space on your laptop or even in a good desktop to actually store the wave function of the system, let alone to solve it. This is just a problem in data. We cannot store the actual wave function of large quantum many-body systems. And if we dig a little bit on this limitation, this essentially stems from the fact that if you think about a quantum many-body Hamiltonian and you write the wave function on a certain basis, like the one that you see there, essentially to know what is your ground state or any state in your system, you essentially need to store all the coefficients that multiply every single element of the basis, and in particular 2 to the L coefficients. So if we somehow find an efficient way of storing all these coefficients, we can surpass this limitation of quantum many-body systems, or at least one of the most fundamental limitations. So the fundamental idea of tensor networks is to find a compressed representation of these coefficients. And you can think that this procedure is very much like when you compress images. So if you have a very high quality image, you have to store a lot of pixels. But if you sort of reduce the quality of your image, you can get something that resembles the original image, but by using a much smaller amount of computational resources. In terms of wave functions, you can think that the original high-quality image is your true wave function, the wave function that you got if you had stored every single coefficient of the wave function expanded in that specific basis. And then this blurry image is the tensor network representation of your wave function, that it does not have as high quality, but that allows you to see essentially all the important features of the wave function. And what is interesting of tensor networks is that there's a single parameter that allows you to systematically improve the quality of the image. So a single parameter that allows you to go from this low quality image to the high quality image. So the basic idea of the simplest tensor network, which is a matrix product state, is to say that these coefficients of the wave function are essentially written as a product of matrices, as a product of tensors. And if you have L sides, you essentially say that these coefficients can be represented as a product of L matrices with dimension M. This M is what is called the bond dimension of the matrix product state, and it's essentially the quantity that determines the quality of your matrix product state. And essentially, if you fix a single M, the amount of coefficients that you have to store increases linearly with the system size. And this is the fundamental idea of matrix product states, that we can use a linearly scaling amount of resources to parameterize the many-body wave function of a system of size L. And in practice, one essentially represents these tensor networks in the following ways. So you say that every single wave function has, let's say, different legs that correspond to the different spins that you have on your chain. And when you write down the wave function in this form, and in particular, when you go to the matrix product form, you essentially write that every single matrix corresponds to one node. So for those of you working with matrix product state, this is, of course, something that is very familiar for you. Now, there's something very important of this tensor network, which is that, of course, you do not parameterize the whole Hilbert space. You only parameterize a very small part of the Hilbert space, which in particular is the states that follow an area law, or the states that have a finite entanglement entropy. It turns out that this is a very good choice for Hermitian models, but we do not know yet for non-Hermitian models. So in practice, this matrix product representation tells you that your states that are parameterized have a finite entropy, and this entropy is bounded by the bond dimension. And it turns out for that one-dimensional Hermitian problems, this is actually a wonderful approximation. And this has been used for many, many years for grounded states, excited states, time evolution, typical minimally entangled thermal states, and many other techniques. And matrix product states has been the most powerful method that we have for one-dimensional models, and it has been a very competitive method even to go to two-dimensional systems. Now, of course, we are interested in non-Hermitian physics. So there are two very important questions. First of all, do matrix product states provide a good parameterization of non-Hermitian wave functions, and in particular of the non-Hermitian grounded states? And this is a question that is actually extremely critical, but we don't know the answer yet. The approach that I'm going to take today is we are going to try, and we are going to see what happens. And it turns out that they apparently work very well in many cases. We do not know yet in which regimes they are extremely good, but for all practical purposes, we can even use them in this non-Hermitian case. And then the second question that we need to answer that will be very relevant for those of you using matrix product states is how we actually find the grounded state and excited states using tensor networks. And the basic idea is that you can think that these matrix product states are just a variational wave function, and you can optimize them in any way you want. You cannot use density matrix normalization group, but you can use any other optimization algorithm. And in particular, you can use Arnoldi-Krylov algorithm to find grounded states of non-Hermitian systems. And the last thing that I would like to point out is that even though today I'm going to focus on matrix product states, all the ideas that I would like to show you can actually be exploited also with other types of tensor networks like PEPs, or even with neural network representations of quantum or quantum many-body states. So these ideas are actually very promising with many other many-body solvers. Okay, wonderful. Now let me tell you about dynamical excitations, which are essentially the fundamental idea that we would like to focus on today. If you think about single particle Hamiltonians and many-body Hamiltonians, there are some very specific differences that make them actually hard to understand simultaneously. So in a single particle Hamiltonian, if you have L sites, you have L eigenstates and L eigenenergies. Now, in a many-body Hamiltonian, if you have L sites, you have 2 to the L eigenenergies and 2 to the L eigenstates. So this mismatch between the number of eigenstates and eigenenergies actually comes from the fact that in a single particle model, you capture only a certain set of excitations, whereas in a many-body model, you capture a much bigger set of excitations. And in particular, in a single particle model, we capture single particle excitations, whereas in a many-body model, we can capture single, 2, 3, up to let's say as many as we want. So a fundamental question is, how can we go smoothly from a single particle model and to a many-body model, and specifically how we can identify the topological modes in a many-body model in a way that it's compatible with our understanding with single particle excitations. So for this, we can use dynamical correlators. And the basic idea is that a dynamical correlator is essentially a quantity that tells you which excited states have one more or one less electron than your grounded state. So you do not look at all the excited states, but you only look at those that have a certain subset of excited states. And mathematically speaking, you can actually simply write this down in terms of this formula that you see here. So you take a delta function that essentially picks only the excited states that have a finite energy difference with respect to your grounded state, and then you compute this matrix element. So you take your grounded state, you create an electron, or you annihilate an electron, and you compute the overlap with the excited state. This quantity is directly what it's called a dynamical correlator, and usually it is more convenient to write it in terms of the full Hamiltonian instead of in terms of the eigenstates. And in that case, the formula for a dynamical correlator looks like this. So you take your grounded state, annihilation operator, delta function, accretion operator, and your grounded state, and this quantity tells you what is the density of excited states that have one more or one less electron than your grounded state. This dynamical correlator in the single particle limit corresponds just to the density of states, and in the many-body limit corresponds to the generalization of the density of states to a many-body Hamiltonian. And we can apply this not only to fermionic Hamiltonians, but also to spin models just by replacing spin operator by fermionic operators by spin operators, as in the formula that you see on the bottom. And these two formulations are actually equivalent if you transform fermionic Hamiltonians to spin Hamiltonians using a Jordan-Wigner transformation. Okay, so now let me show you a very simple example. So let's take a one-dimensional chain, a one-dimensional Heisenberg model with spin 1/2, and let's look at the spin correlator, at the dynamical spin correlator. And the point is that to compute this correlator, it is in principle very easy to write it on a paper, but we actually need to do it computationally. And the basic idea is that one can actually expand this delta function in terms of a polynomial basis. And specifically, Chebyshev polynomial bases are extremely powerful for doing these types of expansions. This is something that people have known for a long time in the case of single particle physics. And this is a method that was originally developed for looking at disorders, single particle models. And this is something that we can actually directly extend to the many-body case, and in particular with tensor networks. The biggest advantage of computing these dynamical correlators with the Chebyshev method is that there's a recursive algorithm that allows you to systematically compute all this expansion. And this is something that it is implemented in this library that you see on the bottom, and that you can very easily use for any one-dimensional interacting many-body model. Okay, so let me show you here two specific cases. So on the left, you can see the case of a spin 1/2 chain. And in particular, in the case of a spin 1/2 chain, we know that this is a gapless system. So the system in the thermodynamic limit has no gap, and it has excitations that correspond to spin-on excitations. And the modes that you see here on the left are essentially the confined modes of a finite chain with vorticides. And on the right, you can see the spin 1 Heisenberg chain. This is what it's known usually as the Haldane model, and it's a well-known model because it has topological order. And specifically, this topological order gives rise to a gap in the bulk and gapless excitations on the edge. This model does not have a single particle analog, but this dynamical correlator allows you to directly see the emergence of H modes in a purely quantum many-body system. This is the reason why we are going to use this in the case of many-body interactions. Okay, wonderful. So now let me briefly show you how one can use systematically this method to look at generic interacting models, and specifically even to models that do not have translational symmetry. So as many of you know, if you have models that are quasi-periodic, or that they have a modulation in space that it's not commensurate with the lattice, we can actually map these models to a two-dimensional quantum Hall effect. So the basic idea is that you have a two-dimensional lattice model with a magnetic flux. There's a transformation that essentially brings this two-dimensional model to one dimension by creating a potential that it's quasi-periodic with the lattice. And this mapping is what gives rise to the so-called Henri-André-Harper model. What is important to note is that this mapping is valid in the single particle limit, but we do not know if it is valid in the many-body limit. And the reason why this mapping has been, let's say, very interesting for condensed matter physicists, because it is a very simple way to understand why some quasi-periodic models have H modes. So now the question that I would like to answer is whether if quasi-periodic models that have many-body interactions still retain the topological excitations that present in the single particle limit. And for doing this, we can just take a one-dimensional many-body model, like a spin chain, with the Hamiltonian written on the bottom, and we can see if there are H modes or not. And to look at these modes, we are going to use the dynamical correlator, of course. And we can do this for spin 1/2, spin 1, spin 3/2, spin 2. It doesn't matter. Tensor networks work very well for all these regimes. Okay, so let me show you what is the fundamental idea. If you look at a very specific case, what you see in the dynamical correlator, it's a picture on the left, is that a gap opens up in your system, and on the left, you have a mode inside the gap, and on the right, you have another mode inside the gap. And these two modes are essentially the H states of the parent two-dimensional quantum Hall Hamiltonian. If you start changing the phasor of your Hamiltonian, that essentially shifts your potential with respect to your lattice, these two modes are going to pump through the gap. And this pumping through the gap, it is essentially associated to the finite Chern number of the parent Hamiltonian. Let me emphasize that this picture on the left is already for an interacting Hamiltonian. So you can see that in the interacting limit, topological modes within the gap still exist. And you can look systematically at how these modes pump with the gap. So you can see at how the spectral function on the left edge evolves with the phasor, how the bulk gaps evolve with the phasor, and how the topological excitation on the right evolves with the phasor. And you see that topological H mode pumps through the gap at the edges, but the bulk remains all the time open, which is what we knew that happened for single particle models. You can see that these systems actually develop gaps in all for different values of the quasi-periodic modulation. And for all these values of the quasi-periodic modulation, you see H states. And in particular, for all these values that appear in this white region here. And this is, of course, something that one can systematically do for higher spin. In particular, for spin 1, you see very much the same phenomenology. A gap appears in the bulk. This spectral gap hosts two H modes, and these two H modes pump through the gap as you change the phasor of your system. This phenomenology is the very same phenomenology as it happens in the single particle case. The fundamental difference is that now we look at a many-body system that has no single particle analog. And what is interesting is that if you think about the spin 1 Hamiltonian, this Hamiltonian already had topological H modes, these fractional excitations of the Haldane chain. And now if you have this spin 1 chain in the presence of the quasi-periodic modulation, you can have two topological modes simultaneously, the ones that appeared in the uniform case and the ones that appear due to the quasi-periodic modulation, namely the red ones and the cyan ones. Okay, wonderful. So now we know that with these dynamical correlators, we can see H modes in interacting many-body systems and interacting Hermitian systems so far. So now what I would like to tell you is how we can actually extend this to the non-Hermitian limit. And let me start by telling you a bit how we can actually systematically create a non-Hermitian model specifically for electronic systems. So imagine that you have a single quantum dot that is this black circle on the left, and this quantum dot is coupled to a lead that is this yellow part on the right. The coupling is gamma, the Hamiltonian of the quantum dot is H0, and the Hamiltonian of the lead is H environment. From the point of view of the single particle wave function, we can essentially write that, well, we know that the full Hamiltonian can be written in this way, and by defining a self-energy using a Dyson's equation, we can write down the Green's function of the quantum dot coupled to the environment. Now, this Green function of the quantum dot can be interpreted as the inverse of an effective Hamiltonian, and this effective Hamiltonian essentially is written in terms of the original Hamiltonian, the Hermitian part of the self-energy, and the non-Hermitian part of the self-energy. The Hermitian part of the self-energy gives rise to a renormalization of the Hamiltonian, and the non-Hermitian part of the self-energy gives rise to a non-Hermitian term in the Hamiltonian. What is important to note from here is that one can think that every time that you couple a quantum dot or an isolated system to an environment, you can essentially create a non-Hermitian term, which is, of course, something that it is systematically done for many in this field. Okay, so from now on, let us just think in this way. We have an Hermitian part of the Hamiltonian, and we have a non-Hermitian part that depends on the coupling. What is interesting of this idea is just by controlling the coupling of the individual system to the environment, we can tune what is the size of the non-Hermitian part of the Hamiltonian. And this is what we are going to do next. So now imagine that you take, instead of a single quantum dot, a chain of quantum dots. And this chain of quantum dots each one is coupled to a different lead, and the coupling to to each lead is different. And specifically, we create a coupling that is weak for the first one, strong for the next one, strong for the next one, weak for the next one, and so forth. What this actually creates is an imaginary on-site energy in each site that is site-dependent due to the site dependence of the coupling in each site. And essentially, this creates a non-Hermitian Hamiltonian that has a modulation in the on-site energies, but these on-site energies are imaginary. What is very interesting is that if you make this modulation of the on-site energies in a very specific way, a modulation of the losses in a very specific way, you can create non-Hermitian topology directly from modulated losses or modulated gain plus loss. And the basic idea is that you can take this modulation of, let's say, weak, strong, strong, weak, and repeat it. And this gives rise to a unit cell with 4 sites per unit cell, and this system hosts topological modes. And this is something that you can very easily show at the single particle level. So if you take a system with open boundary conditions and you put these modulated on-site energies, you get edge states, which is essentially these states that you see here at 0 energy. So the x-axis is the strength of the non-Hermiticity, and the y-axis, the real part of the energy. If you don't have any non-Hermiticity, you have just a pristine one-dimensional chain. If you have non-Hermiticity, you start getting this modes inside the gap. And what is important is that they are 0 modes, and they do not require any fine-tuning in the losses. This is at the single particle level, and this is something that was known since a few years ago. So now the question is, do these modes survive when we include many-body interactions? And this is, of course, extremely relevant in an experimental realization. If you think about quantum dots coupled to leads, very often quantum dots have strong Coulomb interactions, and the fate of the edge modes in the presence of these Coulomb interactions will determine whether if you can see these edge modes or we cannot. Okay, so as a reminder, let me point out that if we close the system, so if instead of using open boundary conditions, we use closed boundary conditions, these 0 modes disappear. So we need to find some way of distinguishing between open boundary conditions and closed boundary conditions once we introduce many-body interactions. Okay, so let us now take our original Hamiltonian that had the single particle term that was kinetic energy plus this modulated loss, and now we add many-body interactions. And the many-body interaction that we are going to add is the simplest many-body interaction that can be written. So a first neighbor density-density interaction. That would be the type of interaction that appears due to, let's say, Coulomb interaction between different quantum dots. And now we want to take this Hamiltonian and we want to see if the H modes remain or not. Once we add this interaction term, we can no longer solve it as a single particle Hamiltonian, and we must solve it as a purely many-body Hamiltonian. So now the basic idea is the following. So now that we have a many-body Hamiltonian, we can look first at the many-body energies, which is what I am showing you here. So in the case of V equal to 0, we are in the single particle limit, namely that we do not have any type of many-body interactions. And in this case, what you see is that there's a ground state here on the left, and there's a big gap, and this ground state is singlet degenerate. Once you add many-body interactions, that is the picture on the right, so many-body interactions on the order of the hopping, you see a very similar picture. There's a single ground state, that is this blue point on the left, there's a spectral gap, and there's no other state with the same real part of the energy. So at a simple glance, it seems that the degeneracy of the ground state is the same when you have no many-body interactions and when you have finite many-body interactions. And this is something that one can systematically look by slowly ramping up many-body interactions. So what I'm showing you here is essentially the two plots from before plus all the intermediate cases. So the color in the plot corresponds to the value of the many-body interaction. And you see that regardless of which many-body interaction you take, you always have a state that is single degenerate, that it's the ground state, a spectral gap, and then a set of excited states that of course depend on the many-body interaction. This is with closed boundary conditions. So with closed boundary conditions, we do not expect any H state. And what we know is that in the presence of many-body interactions, no gap closing happens with closed boundary conditions. If you now take open boundary conditions, the case is completely different. And a simple way of looking at this is by taking the interacting Hamiltonian and slowly changing the boundary conditions from closed to open. So here the parameter T tilde essentially parameterizes whether you have open boundary conditions that corresponds to T tilde equal to 0 to closed boundary conditions that corresponds to T tilde equal to 1. For closed boundary conditions, you have a single ground state with a real part, with a minimal real part of the energy. And once you go to open boundary conditions, then you have several ground states that have the same real part of the energy. Now, the question is that so far we can only see many-body H states and many-body energies, and we want to look at the H states. We want to look at the local density of states at the observable that one could see using tunneling, for example. And the simplest way of looking at this observable is by computing this matrix element between the manifold of ground state, between the manifold of states that have the same real part of the energy. And without entering into details, I would like to just point out that this is essentially proportional to the differential conductance at zero frequency, so to the zero bias conductance. So now we can compute this for different values of the interaction, which is essentially what you see in the y-axis, and the x-axis is essentially the size of the system. And what you see is that at zero many-body interactions, you have, of course, your H modes. And as you increase the many-body interactions, either attractive or repulsive, the H modes remain. And this happens for relatively small systems already, like 8 sites, and it seems that still happens to 12 systems. And these two cases is something that we can solve exactly using exact diagonalization. But of course, what it's interesting to note is whether if this phenomena survives in the thermodynamic limit, so in the limit in which our systems are extremely large. And in this case is when we need to use tensor networks. So let me show you a first benchmark. So here I'm showing you how this zero bias conductance looks like for a small system that we can solve simultaneously with exact diagonalization and tensor networks. And you see that the agreement is, well, is perfect. You get exactly the same profile with exact diagonalization and tensor networks. Now, with tensor networks, you can go to much bigger systems, and in particular, you can go to length scales in which the edge modes do not interact with each other. And if you do that, you see that once you go to 24 sites, you get very well localized edge modes at the edges, and you can go even to bigger systems and see that effectively, once the system is large enough, you get two topological excitations at the edges that are completely isolated and that decay exponentially as you go towards the gap. Okay, so this is essentially how we can see edge modes using tensor networks. But now what would be interesting is how it actually looks like when we not only measure the differential conductance at zero bias, but at any finite bias. And this is essentially what I'm going to show you now. So let's imagine now that we consider a more generic model. So this is essentially the same model as before, but now we introduce another degree of freedom, the possibility of having, let's say, left hopping different from the right hopping. Having this non-reciprocity is challenging for an electronic system, but let us focus just on the fundamental Hamiltonian. And this is going to be important because non-reciprocity, so different hopping towards the right than towards the left, gives rise to skin effect. So our Hamiltonian is going to look like very much like the previous one. So we will have many-body interactions, local loss, and now we are going to have non-reciprocal hopping. And we can think about this Hamiltonian both in a spin basis and fermionic basis, but for the sake of concreteness, let us focus on the fermionic one. Something that is important to note is that in a non-Hermitian Hamiltonian, our spectra is no longer real. And this is actually a problem when computing dynamical correlators, because the dynamical correlators are easily defined if you have a real spectra, but if you have a complex spectra, as it is the case of non-Hermitian Hamiltonians, the conventional formulation breaks down. So now the fundamental idea is actually relatively simple. And even though this slide looks a little bit intimidating, let me walk you through it. Now, if you have a spectra that has both real part and imaginary part of the energy, you need two delta functions instead of just one. So instead of having just a delta function of the energy, we have a delta function of the real part and a delta function of the imaginary part. So this is the first important point. The second important point is that in a non-Hermitian Hamiltonian, left eigenstates and right eigenstates are different. And this has to be taken into account when defining the dynamical correlator. If you take care of all these subtle differences, you can actually do a kernel polynomial expansion by defining our hermitrized Hamiltonian and computing the right matrix element of the derivative of this kernel polynomial expansion. It is a little bit more subtle than in the Hermitian case, but it can be done. And if you do it, you can compute these dynamical correlators in the non-Hermitian limit. Okay, so for the sake of concreteness, let us focus on the Hamiltonian that I mentioned before. That is the equation that you see on top. And I will compute the full dynamical correlator. That is the equation that you see here. And the most important thing for you to remember is that if you integrate this function in the imaginary axis, you recover the density of states of a Hermitian Hamiltonian. So in short, there's a correspondence between Hermitian Hamiltonians, even single particle cases, and the many-body non-Hermitian Hamiltonian. The local density of states is going to be our local dynamical correlator, the local non-Hermitian dynamical correlator. The total density of states is going to be the total non-Hermitian dynamical correlator. So the very same phenomenology that we can understand from a local density of states and total density of states in a single particle limit can be understood with these non-Hermitian dynamical correlators. Okay, so first of all, let me show you how the total dynamical correlator looks like. So this is for a finite system. And as you go from the left to the right, what is happening is that the topological gap of the system is becoming bigger. So specifically, once you are at the very right, what you see is that your dynamical correlator peaks at two different energies that are degenerate, whose real part is degenerate. This is essentially telling you that you have a degeneracy in the real part of your many-body Hamiltonian, very similar as what we can look at in a single particle system that has a topological degeneracy due to edge modes. What is even easier to understand is if we look at the local dynamical correlator. And again, as we go from left to right, what's happening that the topological gap is becoming bigger and bigger. And specifically, if you focus first on the right, what you see is that you have topological zero modes at the edges, at the left edge and at the right edge, that coexist with a topological gap in the bulk. And you can think that as you go towards the left, then these two edge modes hybridize and they go to finite energies. That is very much the same phenomenology as in a single particle system. Those were, of course, relatively small systems. Now we can use this very same method with tensor networks and go to much bigger systems. And here you can see, for example, the case of an interacting non-Hermitian model with 24 sites. And essentially, the phenomenology that you see is exactly the same. You have two edge modes, one on the left, one on the right, that are at zero energy, and then there's a gap that appears on the bulk. The very same phenomenology as in the single particle non-Hermitian case, the very same phenomenology as in the interacting Hermitian case. And this is even easier to see if you compare the dynamical correlators of a gapless case with this topologically non-trivial case. So in the gapless case, you essentially see your confined modes that you can think that are, let's say, particle in a box states of non-Hermitian Hamiltonian. And in the topological case, you see your gaps living together with the edge modes. Now, there's one last thing that I want to tell you, which is what happens if you have skin effect. And the basic idea is that even if you have skin effect, you can actually use this very same formalism to compute the dynamical excitations. And the fundamental idea is that in the presence of skin effect, your right eigenstates are located in the opposite side as the left eigenstates. And given how the dynamical correlator is defined, this essentially tells you that the dynamical correlator is not going to suffer from any sort of skin effect, but is actually going to factor out this accumulation on one of the edges. And if you do the calculation again with tensor networks, what you actually see is that both for small systems computed with exact analyzation and large system computed with matrix product states, you have edge modes. So the algorithm works both in the presence and absence of skin effect. And now, in the last minute, let me tell you about something that is not exactly physics, but something that could be useful for people to reproduce some of these calculations. So first of all, we, of course, we developed a library for doing all these calculations, and these libraries are openly accessible. And specifically, there's a library called the emergence that is a Python library that allows you to solve generic interacting models using both exact analysis .
I think José is freeze at the moment.
Yeah. Apologies for this interruption. It seems that there was a problem with the connection. José, would you mind starting off again when you started talking about the Python code?
Oh, yes, sorry for the technical issue. So you can hear me well now. Yes, great.
Perfect.
Okay, so let me go back. This is the Python code that allows you to solve generic many-body systems using tensor networks, and it works both in the Hermitian case and the non-Hermitian case. And if you are interested in computing dynamical excitations with tensor network, there's a wonderful library developed by Wanse Chen, that is this non-Hermitian KPM.Julia, that allows you to solve, to compute the dynamical correlator that I showed you before. And the last point is that if you would like to solve non-interacting models that are Hermitian, you can use this user interface that does not require any coding, but you can set up the Hamiltonians just using buttons. And the simplest way of explaining how this works is by showing you a video. So here you can see how one can use this interface. So you can select the system, you can add different terms to the Hamiltonian, like kinetic energy, interactions, spin orbit coupling, exchange field, and then press different buttons to see different observables, like band structure, density of states, topological invariance, let's say very curvature, and all the things that one can do with single particle systems. So with this, I would like to finish. And if I could ask you to remember something, please remember that with tensor networks, we can look at excitations in interacting non-Hermitian models. And thank you so much for your attention. And if you have any questions, I look forward to them.
Thank you very much, José, for a very nice presentation. We are now looking, the floor is open for questions, so you can raise your hands. And then, yeah, we have one question from Lovi, please.
Yeah, hello. Thank you so much, José, for this wonderful layout for how one actually handles the interacting systems, also with the non-Hermiticity. So actually, I'm mostly from the single particle. So I have just one naive question, like in the single particle, as you also showed, like the correspondence between the interacting and non-interacting with this dynamical correlator. So I'm just wondering, with the dynamical correlator, you were able to see these edge states. So I'm just wondering if there is a way that you can actually also define some topological invariant from the many-body wave function. Is it also possible that because I was just thinking if this topology can be captured by some many-body wave function that you define some many-body Berry curvature, but I don't know much about it. I'm just wanted to know your views about it.
Yeah, I think that's a really wonderful question. And the short answer is that in principle one could, but probably one would need a formulation of the topological invariant with Green's functions. So as you know, in the single particle limit, we define the topological invariant with the occupied wave functions. Mm-hmm. But in the many body case, there's no notion of occupied wave functions. You have just the ground state, and that's all.
Yes.
Exactly. So if one essentially formulates the topological invariant with Green's functions, it can be done in the many-body limit, and this is something that it can be done in the Hermitian case, and in principle, that very same extension could be done in the non-Hermitian situation. We have not done it, but from the technical point of view, it could be done.
Okay. So then I think in the last part, just to quickly finish, where you showed this skin model, like the non-Hermitian skin model, then probably you could also think along the lines that there is some kind of a bulk boundary correspondence breaking also in the many body cases. I think that can also be inferred from the single particle case. So in the single particle case, you have like this bulk boundary correspondence breaking in the skin effect. And I think one can also think along the same lines in the many body case, that you also have like something like this breaking up.
Yes, absolutely.
Okay.
So that,
Okay.
Thank you.
Okay, thank you.
Okay, our next question can be asked from Clara.
Thanks very much for this very interesting and exciting talk. So I have a question about so you talked about matrix product states, and I know that quite often people use the singular value decomposition there to identify which are the relevant bits essentially to keep, or which are the most dominant ones. On the other hand, for example, also we have used the singular value decomposition in one-dimensional non-Hermitian systems that are not interacting yet to establish a kind of bulk boundary correspondence. So there are then edge states in the scene which are now in singular vectors. So I was wondering if there might be a way then to kind of transfer this knowledge also now to interacting systems where you now use your matrix product approach. So maybe matrix product state approach. So just a very general question. Have you thought about this at all?
Yeah, thanks a lot. This is also a very good point. And there's a very interesting thing that in principle, the singular value decomposition of the MPS is different than the one that one would do for the non-Hermitian case. And the most extreme case is that if you have even a, let's say, single particle model, from the point of view of an MPS, this can have a relatively complex singular value decomposition in the sense that it has, let's say, many eigenvalues that are non-zero. So even a single particle system that one would consider weakly entangled from the MPS point of view can be relatively entangled. I am not aware of any mapping that allows you to go from the SVD of the non-Hermitian model to the matrix product one, but of course there could be some relationship there, and that may be something very nice to look into more detail.
Okay, thank you.
Yeah, thank you.
Okay, José, please go ahead.
Hi, José.
Hi.
Great to see you.
Hey, yes, very nice to see you.
Yes.
Yeah.
And thanks a lot for the nice talk. I have a little bit of a kind of a question related to it all non-Hermitian in general and topology in non-Hermitian in general. So usually, at least all of these skin effects, you could just think of the fact that in the end you have, by the non-Hermitian part, many modes that dissipate faster, such that you end up with those that live longest at the boundary, right?
Mm-hmm. Yeah.
And all in all, non-Hermitian Hamiltonian would not conserve probability of your density matrix, etc., etc. Can you think of how to take your analysis to Liouvillean?
Yeah, that's a really good question. And of course, the formulation that we used for non-Hermitian systems, it is an approximate one. So even if one thinks in terms of non-Hermiticity coming from a self-energy, the self-energy is frequency dependent. And for all this formalism, we assume that the self-energy is frequency independent. This can be a good approximation if, for example, your quantum dots have a hopping that it's much weaker than the bandwidth of your lead. But in generic cases, this is not the case. And in those generic cases, of course, a Liouvillean would be the right way of approaching this problem. In principle, one could use a kernel polynomial expansion also if you have a Liouvillean. It is going to be much more numerically demanding, but it is formally possible. We have not done it, so I cannot say, let's say, how big systems one could reach with that, or if there are some other technical limitations, but in principle, it's something that could be attempted.
Mm-hmm. Okay, I mean, we tried at a certain point to look at something with a thermal one, and there are some assumptions in the literature that seem right. So maybe when we want that, it would be funny.
Yeah, absolutely. Okay. That would be something very interesting to try. Yeah.
Yes.
Yeah. Thanks.
Okay, do we have further questions in the audience? Let me also check the YouTube, so we don't have any questions on the YouTube. I have one question. So in principle, so you have a dynamical correlator. This dynamical correlator has a frequency, and this frequency is effectively treated in a real part. Can we have it in a complex version of that? So in principle, you have two deltas, and then for each delta, you have one real part, so that you have a real and imaginary part. Can we have a complex omega and also complex energies?
Yes, absolutely. And the original formulation of the kernel polynomial method is with, well, the original formulation for the non-Hermitian case is with the real part of the energy and the imaginary part of the energy. So you have a variable, a function that is depends on both real part and imaginary part. Now, in some of the plots that I showed you, I essentially integrated over the imaginary axis. So that's why it depended only on the real part. But in general, it is, of course, going to be a function of both real and imaginary. Yeah, thanks.
I see. Nice. Do we have further questions? I don't see any anymore. So I would say that we probably should thank José once again, and also all the participants for being attentive. Our next speaker would be Angelo Carollo on the 19th of July. So we look forward to seeing you there as well. And thank you all for participating, and see you in 3 weeks.
Yep, thanks a lot. It was a real pleasure. It was wonderful. Thanks.